Hello everyone, in this video let us try and solve this problem. A W24 by 370 simply supported steel beam is uniformly loaded with a dead load of 1 kip per feet and a live load of 2 kip per feet. The beam is 10 feet long, supported at each end. Determine if the beam's flexural strength is sufficient to carry the load. Use LRFD, Fy is equal to 50 kSI and E is equal to 29 kSI. So let's start the solution. Okay. First, we identify if the problem uses a built-up or a non-built-up section. So from the given, we're using a single shape, which is a W24 by 370. And it simply states that it uses only one. So it's not a built-up section. No? So it's not multiple of this. It's only one W24 by 370. So it is not a non built up section. Okay, so it is a non-built up section. Next, we need the properties of our W24 by 370. So we need to go to our steel manual PDF, which I provided to you in your module in Canvas, which can be found specifically on page 1 to 18. We have uh, the depth, which is 28 inches, the thickness of the web, which is 1.52 inches, the depth of the thickness, the depth of the flange, which is, or the width of the flange, is 13.7 inches, and the thickness of the flange, which is 2.72 inches. Thickness of the flange, thickness of the web, thickness of the flange, the width of the flange, and the depth of the beam. Or we can also have it as H. Now, either way, D and H, it's just the same. Now, first we do is we do the checking. If our beam is compact or non-compact. So we need to do the checking with the H over the thickness of the web. If it will less than 3.76, we have E over Fy to the power of 0.5. While the other checking is the width of the flange all over 2 times the thickness of the flange, and 0.38 E over Fy power of 0.5. So we need to first check these two values if it will satisfy a compact or non-compact beam. So the H is 28 over thickness of the flange is 1.52, question mark 3.76. E is 29,000. We have Fy is 50 to the power of 0.5. Okay, so the BF is 13.7, 2 times DF is 2.72. We have 0.38, 29 all over 50. This is the power of 0.5. So we check these values in the calculator. We have 28 divided by 1.52, so is 18.42. It's now 18.42. While the other one, you have 13.7 over 2 times 2.72. 2.72, the answer is 2.52. 2.52. Now let's check 3.76 all over 29,000 all over 50 to the power of 0.5. Oops, 0.5. Okay, 3.72, 29,000 of 0.5, 90. So we have 90.55. So So this is 18 is less than 90. We have 0.38. 0.38. 9.15. 9.15. So 18 is less than 90. We'll also have 2 is less than 9. So since both are less than, then we have a compact beam. Okay, so we have a non-built up and a compact beam. So let's start with step 1 using the non-built up, using a non-built up compact beam solution. Step 1 is we solve the ultimate uniform. We need to solve the required maximum moment starting with the ultimate uniform load. So let's have it here. Uniform load ultimate. Since we're using LRFD in the sign, we will get 1.2 of the dead load. The dead load is 1. Okay. So 1.2 times 1 plus 1.6 of the live load. The live load is 2. So 1.62. So we have the ultimate uniform load, 1.2 times 1 plus 1.6 times 2. This is 4.4. 4.4 kip per feet. Okay. Next, we know from the problem that it is a simply supported beam. So simply support. Simply support meaning if we have the beam right here, we have one support on one side as pin, the other support on the other is roller. And since this is a uniformly loaded, so we have it here uniformly loaded. This is 4.4 kip per feet. Yeah. Now the next thing we need to solve is the maximum moment developed in this beam where it has a pin and a roller support under a uniform load. We need to solve the maximum moment. Normally what we would do is first we would need to solve the reactions. After solving the reactions, we draw the shear diagram and then we draw the moment diagram. Most probably the shear diagram would look something like this one. That's the shear diagram, while the moment diagram would look something like this one. Okay, we have the shear and the moment diagram. The shear diagram and the moment diagram. So what we need is the maximum moment, which can be seen in the moment diagram. We need this value right here. So to get this, we need to solve the reaction, draw the shear diagram, draw the moment diagram, then determine the highest point in the moment diagram or the highest value in the moment diagram. And that is our maximum moment. Now we can do the computations manually, or we can memorize formulas, which is very useful when you will soon arrive for your licensure examination, since as much as possible we need to save time. So for in setups such as this one, we have simply supported uniform load. The formula to solve the maximum moment is simply the uniform load times the length squared divided by 8. Okay? Where we have the uniform load is 4.4. The L from the given is, it is 10 feet long. So you have 10 squared all over 8. So M max, we have the 4.4 times 10 squared divided by 8. So we have 55. Now have 55. Then is kip per feet. This is feet squared. So this becomes kip feet. And this is now our maximum moment. Or this is also our required moment. This is also our required moment, or the moment required by the load. So next we go to step 2. Step 2, we have our length, or the unsupported length is 10 feet since it is supported each end. So the length between supports is 10 feet. So from our steel manual, the same steel manual PDF that I provided to you, go to page 3-20. Page 3-20, no? Go to page 3-20 so that you will be able to determine for this specific shape and for this specific FY, will determine the LP from the PDF, which is we can obtain it from page 3-20 to be 11.6 feet. Okay, and since we have LB is less than LP, if you notice, LB is 10, LP is 11.6, so LB is less than LP. So our M capacity, or the moment capacity of our beam, is equal to the MP value in the PDF. And we have the MP value in the PDF to be 4,240 cubic feet. Okay, this is what we have the value for. Note, this is LRFD. Okay, this is for the LRFD, 4,240 cubic feet. Okay, next we proceed to step 3. Step 3, we compare M capacity and M required. This is the required moment due to the load, and this is the capacity of the shape of our beam. So if we compare, obviously capacity is, M capacity is greater than the M required, which means it is good, no? It can carry the load. Now for step 4, we need to solve the required section modulus. The required section modulus is the moment required, which is we have 55 all over 0.66 of the Fy. The Fy is 50 KSI. Okay, so the Fy is 50 KSI. So 55, this is the M required, all over 0.66 Fy. Now the M required is in cubic feet, while the Fy is in KSI, so cubic per square inch. So let's try and convert all into inches. So this is already KSI, this one is cubic feet, so feet, convert it into inches. We simply multiply it by 12 to have our answers all in inches. Yeah, 55 times 12, 0.66 times 50. Okay, we have our answer is 20 inch cube. That is the required section modulus, no? The section modulus required by our load. This is cubic, this is cubic, this is now inches, while this is in cubic per inch squared. So cancel the cubic, inch times inch squared, it becomes inch cube. Next, for the step 5, we have same from our steel manual PDF, no? From our steel manual PDF, specifically at page 1-19, we can see for the W24 by 370, the capacity of our shape, or the SX. We have the 957 inch cube. Okay, so we have the SX. So if you have to ask, if there are two values, SX and SY, use SX, because normally for this kind of shapes, it will be oriented in a way that SX will be used. So we have use SX, which is 957 inches. Now for step 6, we compare the capacity is 957 while the required is 20. So obviously we have the S capacity is greater than the S required. Okay, so still good as well. So since both the moment and the section capacities are past or greater than its required values, therefore the beam is adequate or sufficient. So therefore the beam is sufficient to carry the load. Okay, since the moment required is less than the moment capacity and the section required is less than the section capacity, so the beam is sufficient to carry the load.